All right, hello, ladies and gentlemen. Today is December 3rd, 2019. We're looking at more models today, more solving exponential growth applications. And so right now I do need you to get those books and copy the graphs and titles on page 355. No, not 355, 255. No. Problems there today with my numbers. Okay, page 255. Remember, on this video, you can pause and rewind as much as you need to because I am going to go kind of fast. All right, so you should have copied down these 6 graphs, and I wanted to talk just a little bit about them. Here we have our regular exponential growth curve. You can see it's base E, and this is what we use most of the time. Base E is a naturally occurring number. We know E is not quite 3, 2.718, blah, blah, blah. And most of our growth population models that we use approximate this curve for a small window of time, small windows of time. But down here, this model, this is what we call a logistics curve. And it has this horizontal asymptote at the top, and it also has an asymptote at the bottom here. And a logistics growth model is more akin to how population actually grows over an extended period of time. But you can see if we were just to look right here, that curve is pretty similar to this exponential growth curve. The problem is most populations don't grow without bounds. So you can think about like a population of fish inside of a lake. So a lake is a closed environment. And so fish will multiply and procreate and get larger and larger, but at some point they'll grow and grow and grow. But then at some point, the food supply is going to become a little restrictive, and therefore we're not going to have as much survival. And so that population gets too dense, and then resources start to wane, and population will then start to decrease. And so we have population growth, and there's this turning point where it then growth declines, actually decreasing growth. And this is more akin to how population actually grows in real life. And you can imagine our population of humans always grows unchecked. At some point, our resources are going to get too small, and well, there you go. This is another important curve. This is the Gaussian normal curve. You might think about it as a bell-shaped curve. This is where we do most of our standardized testing comes from. So like the ACT or the SAT. And what happens is this maximum right here is the average score for the group of test takers, shall we say. And so the highest point is the average, and then it decreases on either side from there. And that's the Gaussian normal curve that we use a lot. We've got log curves. These are the log rides. We talked about those. And here we have our exponential decay model. So these are all the things we're sort of talking about today, and all good things to sort of have an idea about. So example 1, complete the info for a savings account in which interest is compounded continuously. The first group of problems you've got today basically are fill in the blanks. You're given a little bit of information to go on, and it changes each time, so you have to look at what you're given and then figure out the other stuff. So each problem has a bunch of different parts to it. So, look at what you're given and see what we can learn from that. Again, you can pause this at any time if you need to copy down more stuff or whatever. So first of all, they're telling us we're compounded continuously. And since it's compounded continuously, we know we're going to use our PERT model, A equals P times E to the RT. And in this particular problem, they're giving me the initial amount of money. And that initial amount is always the P, the principal, what we started with, that initial amount of money. They're also telling me that I have an amount after 10 years. This is actually 2 pieces of information. This is the amount, A, after 10 years have passed. So they're actually giving me a bunch of information. And let's see, if I plug that in, and for A, I have 1264.45 equals P was 900 times e to the RT. R, I don't know, T is 10. And so you can see just by plugging in all that information, they're going to allow me to solve for R. And so I can do that to find R. I'm going to start by dividing by 900. So I have e to the 10R equals, let me use my calculator, 1264.45 divided by 900 is 1.40, let's say 5. I'm going to just keep this answer running in my calculator because it's really easy to do that. If I want to solve for R, I have to drop down my power, which means I need a natural log of both sides. So natural log of this answer, I can just do right on my calculator, natural log, and then don't forget about your answer button. A and S, answer is the second function, so second answer. And I get 0.33999 equals 10 times R times the natural log of E. Natural log of E is 1, and I just need to divide by 10. And so we're done, divide by 10. We get R equals 0.0330999. It's okay. Well, that's R. But we actually want the percentage rate, the APR, annual percentage rate. R is a number we plug into our model, but the annual percentage rate would actually be 3 I guess we could round to 40. I'm not sure exactly what they'd want it to round to. But that is your annual percentage rate. As a percentage, it would be 3.4%, just about. Now, we also need to find the time to double. Now, finding the time to double means for the initial amount to double. So to find the time to double, I know that my principal was 900, and I want to know how long it takes. So I'm going to find find the time it takes for my initial amount to double. Well, to double means it's going to turn into $1,800. And I know the R now, and the R was 0.034, which I'm just going to convert that R that we found. And a lot of these problems, this is what you need to do. You need to find R first, and then they're going to ask you to do another thing. So now that I know R, I can figure out T. I'm going to divide by 900. 2 equals e to the 0.034 T. I can take a natural log of both sides. So we get 0.034 times T times the natural log of E, which is 1. And then I can divide. So I get the time to double, natural log of 2 divided by 0.034. It's about 20.39 years, roughly. Years to double. So you're not given the same thing every time, but look at what you are given and see what you can learn from that. So each problem has multiple things that you have to find. Okay. Sample 2. Again, you can pause this if we need to copy this equation down. The population P of a city is given by P equals, always a good thing to write down the model, 105,300 e to the kt. Again, this looks just like PERT. A equals PE to the RT. We're just using different letters, but it's all the same thing. P is standing for population. Always good to know, first and foremost, what your letters stand for. And then T is time and years since 1990. So T is years since 1990. And that's really, really important to know. In 1995, Oh, that's interesting. The population was 113,501. They're giving us information there. In 1995, the population was 113,501. Really, that's an ordered pair. They're giving us time and population. But we don't want to use 1995 because T represents years since 1995. So that would be, oh, sorry, years since 1990. This would be 5 years later. So 5 years later, the population is 113,501,000. And that's information that we're going to use to plug in and find K. So most of these problems are going to ask you to find K first. And I'm going to plug that in, plug in the information I know, 113,501 equals 105,300. This would be the initial population. When time was 0, e to the 0 would be 1. And so this is when time is 0, the population was 105,000. That'd be in 1990. E to the k times 5 years later. 5 years later, we had a population of 113,501. I'm going to solve for k. So divide 105, 105, 300. Again, I'm just going to keep that sort of running total in my calculator. I really don't want to round off until the very end. Divided by 105, 300. And I get 1.07788 e to the 5k. And then I can go ahead and take a natural log of both sides. It's going to allow my power to drop down. So I can do natural log of my answer. Whoa, what did I do? Quit. Natural log of my answer. And that is 0.074998. And again, I'm really rounding, saving my rounding to the very end. The 5k drops down. Natural log of e is 1. So we just have to divide by 5. So divide by 5. And I didn't round until the very last thing here. 0.014999, which really would round up. At the U of A, they like you to round to 6 decimal places. So I guess all those round up, and it really just becomes 0.15. All right, so now that's information that I'm going to go and plug back in so that I get a complete model. So that's the second part. We want the complete model. That model would be P equals 105,300 e to the 0.015 t. So there is our complete model. So first we solve for k, then we write the model, and then we answer the question we actually want to know information about. In what year? So in what year means we need to find t. In what year will the city have a population of 120,000? All right, so 120,000 is the p-value. So we want to know when we equal 120,000. Yes, that's right. 105,300 e to the 0.015 t. So again, I'm going to start by dividing. Gotta isolate my base. So I have 120,000 divided by 105,300. You know, watch your zeros. A lot of students type too fast or whatever, and miss a problem because they dropped a 0 somewhere. All right, now to drop my power, I'm going to take a natural log of both sides. So I'm going to do natural log of my answer. And I get 0.130678 equals, my power is going to drop down 0.015 times t times the natural log of e, which is 1, and divide by 0.015. So divide by 0.015, and I get time is about 8.71188 years. So I don't know, I probably just rounded to about 8.7 years to reach 120,000. But they want to know in what year is that? Well, that's 8.7 years since 1990. So about 1998, 1999, closer to 1999 is when that population is going to reach 120,000. All right, ladies and gentlemen, that's it for this. Go ahead and you can start working on CP78. It's going to take some time to do these problems in particular. Read carefully, figure out what you know, plug in what you know, and go from there. Most of these are matching, I think, so that should be fast. But these will take some time. Make sure you follow directions and answer all the parts.